Hey everyone, and welcome to today's Explainer. I am so glad you could join me. Today, we're taking a really fascinating journey into the microscopic world to unlock the secrets of kinetic theory. Seriously, if you've ever found yourself wondering why things heat up, how those massive industrial engines actually work, or even just what's literally happening in the empty air around us right now, you are in exactly the right place. So let's step into this invisible world and uncover the motion that fundamentally governs our universe. Richard Feynman, who is absolutely one of the titans of 20th century physics, once posed this really thought-provoking doomsday scenario. He asked, if humanity faced total extinction and we could only pass down one single sentence to the next generation of life, what would it be? Well, he chose the atomic hypothesis. He believed the single most valuable piece of human knowledge is that all things are made of atoms, and they're constantly moving and interacting. That perpetual motion, that's the beating heart of our entire discussion today. Here's a quick look at our roadmap for today's session. 1. The hidden world of atoms. 2. The core gas laws. 3. Inside the crowded room. 4. Pistons, temperature, and collisions. 5. The equal partition of energy. And finally, 6. Final gas law exam review. All right, let's dive right into Section 1, the hidden world of atoms. Believe it or not, the whole idea of atoms is actually incredibly ancient. Way back in the 6th century BC in ancient India, a scholar named Kinetic proposed these indivisible, ultimate building blocks of matter that he called paramanu. Later, over in Greece, Democritus coined the term atom, which literally means indivisible. And amazingly, some of these early scholars managed to estimate atomic sizes entirely through pure logical conjecture. Crazy, right? But it wasn't until John Dalton in the early 1800s, and then guys like Maxwell and Boltzmann later in the 19th century, that we finally established modern atomic and kinetic theories. Even then, you'd be surprised how many famous 19th century scientists completely doubted the existence of atoms before the experimental proof became undeniable. So you might be wondering, why did those brilliant ancient ideas just kind of stall out for thousands of years? Well, it's because they were mostly intuitive conjectures. They were beautiful, elegant, philosophical guesses, but they were never actually put to the test. The true hallmark of modern science, and exactly what allowed scientists like Boyle, Dalton, Maxwell, and Boltzmann to totally revolutionize our understanding, is quantitative experimentation. They essentially dragged humanity out of the philosophical debate club and into the realm of evidence-based, measurable scientific discovery. Real quick, before we go any deeper, let's just make sure our fundamental definitions are locked in. An atom is the smallest indivisible constituent of an element. Now, obviously, today we know atoms have even smaller subatomic parts, but for basic chemical and thermodynamic behavior, this definition holds up perfectly. And a molecule? That's simply a combination of these atoms bonding together to form a compound. Keeping this distinction clear is absolutely crucial as we start looking at how these tiny little building blocks bounce around to create our macroscopic world. Moving right along to Section 2, the core gas laws. Okay, the ideal gas equation, PV equals mu RT. You've probably seen this one before. It's essentially the macroscopic rulebook for gas behavior. It perfectly explains how pressure, volume, and absolute temperature always relate to each other for a specific amount of gas. If you suddenly compress a gas into a tiny volume, well, its pressure or its temperature simply has to spike to balance out the equation. But to really grasp why a rule like this even exists, we have to shrink our perspective way, way down to the scale of the molecules themselves. Which brings us perfectly to Section 3, inside the crowded room. I want you to imagine a gas, not as some empty, invisible cloud, but as a hyperactive, incredibly crowded room. Picture a huge room full of people running around totally blindfolded. They're constantly bumping into each other and just slamming into the walls. Every single time someone hits a wall and bounces off, they exert a little push against it. Well, on a microscopic scale, millions of tiny molecules are doing exactly this. That collective pushing from all those millions of individual, tiny little impacts, that is precisely what creates overall gas pressure. But there's a huge catch here. If real people repeatedly slammed into walls, they'd get tired, right? They'd eventually slow down and stop. Molecules don't do that. And that's all thanks to the magic of the elastic collision. Gas molecules behave like tiny, perfectly independent, bouncy balls. They crash into each other, they smash into the walls of whatever container they're in, but they literally never lose any total kinetic energy. They never get exhausted. They just keep rebounding forever, maintaining this perfectly chaotic, dynamic equilibrium.
Let's apply this in Section 4, pistons, temperature, and collisions.
So think about this. Why exactly does a gas heat up when it's compressed by a piston inside an engine? It's a huge fundamental question in engineering. Macroscopically, our gas laws tell us that shrinking the volume cranks up the temperature. But mechanically, on a microscopic level, what is actually generating that heat during those particle collisions?
To really visualize this, think of a heavy cricket bat. If the bat is just held completely stationary and a ball hits it, the ball bounces back at its normal speed. No big deal. But if you violently swing that bat forward right as the ball hits it, the ball rebounds much, much faster, right? It gains a ton of kinetic energy. In an engine, the piston is our moving bat, and the gas molecules are the balls. When the piston compresses the gas, it literally smacks the molecules, accelerating them. Faster molecules mean higher kinetic energy, and temperature is basically just a measure of that average particle speed. Understanding these kinetic energy principles is absolutely vital for engineers when they're designing heavy industrial pneumatic tools or figuring out how to build efficient machinery cooling systems to keep everything reliable.
All right, on to Section 5, the equipartition of energy.
Now this brings us to a super cool thermodynamic concept. The law of equipartition of energy basically tells us that a molecule doesn't just hold energy by flying in a straight line. The energy actually distributes itself equally across all possible modes of motion. Think of it kind of like a budget. The energy gets spent equally on moving side to side, which we call translational motion, but also on spinning or rotating around, and even vibrating back and forth like a tiny spring. Temperature ultimately is just the measure of all this chaotic, total motion.
Let's see how this actually plays out across different types of gases. Take a monatomic gas, like argon. It's just a single, lonely atom. All it can do is dart around. Translation, so it absorbs the lowest amount of heat. But a diatomic gas, like oxygen, that's shaped more like a dumbbell. So not only does it dart around, it also tumbles and rotates. That gives it more ways to absorb energy, giving it a medium heat capacity. And polyatomic molecules are even crazier. They dart, they tumble, and they vibrate, meaning they soak up the highest amount of heat. Engineers use exactly these gas collision and motion principles to optimize pneumatic machine cooling in real-world industries.
And that brings us to our final stop today, Section 6, Final Gas Law Exam Review.
Okay, here is your ultimate cheat sheet for the macroscopic laws. We've organized these key concepts into a simple study guide for rapid recall. For Boyle's law, remember temperature is the constant. Squash the volume down and the pressure spikes up. For Charles' law, pressure is the constant. Heat the gas up and its volume expands. And Dalton's law is super straightforward. In any mixture, the total pressure is literally just the sum of all the individual gases' partial pressures acting totally independently.
Let's quickly hit those essential formulas and what they mean in the real world. PV equals mu RT is your big picture macroscopic connection. That second formula, E equals 3/2 kBT, is absolutely critical. It's the bridge to the microscopic world. It mathematically proves that temperature is fundamentally just the kinetic energy of the particles. And finally, the root mean square speed formula calculates exactly how unbelievably fast these tiny particles are zipping around based entirely on their mass and the temperature of the room.
If you're steering down a specific heat calculation on your exam, don't panic, just run through these 3 logical steps. Step 1, identify your gas type. Are we dealing with a single atom, a dumbbell, or something more complex? Step 2, determine its degrees of freedom based on how it can move. Is it just translating, or is it rotating and vibrating too? Step 3, apply the equipartition formula. Just remember that every single degree of freedom contributes a little bit more to that energy capacity. Follow that flow, and you'll nail any core gas law calculation. Take a second and consider the number 100. To put things into perspective, 100 roughly represents the ratio of the mean free path of a gas molecule compared to the normal distance between atoms in a liquid or a solid. What does that mean? It means a gas molecule travels about 100 times its own interatomic distance before it actually collides with another molecule. That massive, crazy amount of empty space proves just how incredibly freely these invisible particles move, and why gases can so effortlessly expand to fill up literally any container you put them in. Let's wrap things up today with a pretty provocative thought, circling right back to Richard Feynman's doomsday scenario from the beginning. If all of our microscopic knowledge vanished tomorrow, how long do you think it would take humanity to rediscover this hidden world of motion? I mean, it took us over 2,000 years to transition from ancient philosophical intuition to the rigorous experimental physics of kinetic theory. The chaotic, bouncing, rotating microscopic world all around us is a hard-won scientific marvel. I really hope this explainer has helped you see the air around you in a totally new, dynamic light. Keep exploring, stay curious, and thank you so much for joining me today.